are the University of Exeter's 2020 IGEM team, and we would like to introduce you to our project, CalcifEXE. The aim of our project is to enhance the natural ability of Bacillus subtilis bacteria to precipitate calcium carbonate using synthetic biology. Calcium carbonate can be found in almost everything, from breakfast cereal to cement. Our project would provide a significantly less carbon-intensive alternative to limestone mining, one of industry's biggest CO2 emitters. CalcifEXE technology has the additional advantage of not being restricted by geology, as it can be used anywhere in the world. By implementing the bacteria into a 3D bioprinter, our project has the potential to revolutionize a number of manufacturing processes. Our custom-made calcium carbonate shapes would have a wide variety of uses in environmental and biomedical fields, an example being calcite-based bone regeneration in implant dentistry. Although these applications also extend to industries as diverse as the cosmetics and paper industries, our team is focused on using CalcifEXE technology to aid the migration and rejuvenation of coral and reefs. With coral reefs living under the increasing threat of ocean acidification, CalcifEXE could provide a 2-for-1 advantage, producing scaffolding to help the corals regrow and survive, all whilst massively reducing the carbon cost. As a Centre for Coral Reef Research, University of Exeter has provided us with a wealth of knowledge on coral, allowing us to build up a detailed understanding of the coral rejuvenation process. Throughout the project, we have ensured that our work is taken out to the wider community with public interest in mind. We maintained consistent communication with the general public, other IGEM teams and experts, for example by taking part in a coral symposium set up by the fellow IGEM team from the University of New South Wales, where we presented to an international community of varying scientific knowledge. After the symposium, we received emails from interested parties. This allowed us to share more information about our project and to understand the influence of our project on a global scale, opening up a two-way dialogue. One of our main priorities has been making certain that our innovation was responsible and socially desirable.
We began our IGEM journey with a long list of potential project ideas, ranging from the desulfurization of crude oil to the biodegradation of plastics. After consulting many industry experts and doing some market research, we became interested in the concept of bioconcrete, a type of self-healing concrete which relies on calcium carbonate precipitating bacteria to heal cracks. Mining natural calcium carbonate for cement, such as limestone, has a huge carbon footprint, contributing around 18% of total carbon dioxide emissions from industries. The rising threat of climate change means that coming up with innovative and sustainable ways of material production is now more important than ever. By using a biological approach as opposed to traditional calcium carbonate production methods, we save on large amounts of CO2 being emitted into the environment. As we continued with our research, we realised that UK legislation concerning living bacteria within concrete would significantly hinder the progress of our project. We decided that instead of integrating our bacteria in concrete, we would combine the bacteria with a hydrogel to make an ink, which could then be used to 3D print calcium carbonate. But what exactly is the mechanism behind this process? By genetically modifying the Bacillus subtilis bacteria to produce exogenous enzymes, we aim to upregulate carbonate production. These carbonate ions would then react with calcium ions, which are present in the culture medium, to form calcium carbonate crystals. The other component of the ink is a hydrogel, which is primarily made up of water alongside polymer chains to increase the viscosity. Therefore, integrating the engineered bacteria into our hydrogel will make the resulting calcium carbonate adaptable for various uses, as in medical fields, for example in dentistry. Our project, however, has a more specific goal in the world of marine biology, in particular coral reefs. The world's coral reefs are increasingly endangered havens of biodiversity. This is due to many things, including climate change and destructive fishing practices, which upsets the delicate balance of many marine ecosystems. We therefore devoted a key part of our project to aiding the rejuvenation of the world's coral reefs. We aim for our 3D printer to print highly specific coral reef backbone structures, which will aid corals to continue to thrive. So has it been just us alone? Nope. This year, our team has reached out not only to other IGEM teams, but also to schools and industry experts. Collaborating with schools has given us the chance to introduce the world of SynBio to younger students, which we hope will inspire them to become scientists of the future. Because the focus of our project has been specifically about corals, we've been able to talk to many coral experts. Professor Mike Allen from the Plymouth Marine Laboratory and Professor Steve Simpson here at Exeter are just two of the many people we have collaborated with. Overall, we didn't let the unusual circumstances affect our dream of creating an innovative new product.
Due to the pandemic, we were incredibly lucky to get lab access, albeit for a short period of time and under significant restrictions. For our microbial-induced calcium carbonate precipitation, we decided to use a multi-enzyme approach in a Bacillus subtilis chassis. Firstly, we chose two carbonic anhydrase enzymes originating from different sources. Carbonic anhydrase catalyzes the conversion of atmospheric carbon dioxide and water into carbonic acid, protons, and bicarbonate ions. The carbonic anhydrase is the enzyme that will lead our project, being carbon mitigated compared to industry. The second type of enzyme we investigated and chose was a urease, responsible for urea hydrolysis. The products of that reaction can equilibrate in water and produce bicarbonate ions and hydroxide ions, among others. The bicarbonate ions produced by both enzymes are free to bond with calcium ions to make calcium carbonate. We hope then, by expressing both of these enzymes on top of Bacillus' native urealytic pathway, we can increase calcium carbonate biomineralization. The final group of proteins we aim to transform into Bacillus are naturally found within the genome of the very corals we aim to save. Coral-rich chaperone proteins from Stylophora pistillata seem to have a role in composing the coral's organic skeleton matrix, doing so by mediating the calcification by catalyzing the reaction between calcium ions and carboxylate molecules. Although these carps have been previously studied in IGEM, they were only investigated as a complete operon, so we wanted to explore the impact each of these proteins have on the rate of calcium carbonate biomineralization. We used type 2S molecular cloning to join our parts and combine our complete genes in our destination plasmids. These were transformed into E. coli DH5-alpha, subsequently extracted, and then experiments were performed to transform them into our terminal Bacillus subtilis WB800N chassis. If it were not for COVID, we had planned to combine our genetically engineered bacteria with a hydrogel to form an ink for our 3D printer. Our printer design had chambers for the hydrogel and the Bacillus subtilis spores. When these were mixed, the water in the hydrogel would revive the bacteria and initiate calcium carbonate precipitation.
As we didn't expect any time in the labs, we were relying on the modelling side of the project to guide our real-world implementation. The 3 models we have produced have given us invaluable information about the steps we would need to take when using hydrogel in the ink, and have also informed us about the extent to which our carbon mitigating technology would reduce global emissions. The first code we developed was written in MATLAB and represents the CO2 diffusion through the hydrogel. This informed our research on the size and distribution of the ink we could realistically print. We made key assumptions with the diffusion, such as the gas moving throughout the hydrogel in a Brownian motion, and that the viscosity of the medium is uniform throughout. By combining the implicit finite differences method, boundary conditions, and fluid dynamic theories, the code creates a 2D model of how the CO2 gas diffuses through the hydrogel, and allows us to understand the limits of the shapes we would be able to print with the ink. Our second code focused in on the mechanical properties of the hydrogel itself. Having modelled the CO2 diffusion through it, we then wanted to analyse the viscoelastic effects of the fluid, as these factors are imperative to understanding how the physical properties will affect bacterial mixing, as well as the rate at which printing can occur. We found when a hydrogel is stretched to a significant fraction of its original length, the stress forces cease to increase, unlike a simple elastic material. The results of the model show that the viscoelastic property of a hydrogel containing 90% water makes it a suitable choice of material for use in a bioprinter, as we found it would print at a sufficient pace. Having developed both of these models, we realised how critical analysing the data from global and UK CO2 emissions would be. This would further our understanding of how beneficial our carbon mitigating technology is to the world. We statistically analysed both UK and global emissions, and calculated it would take only 1.15 tonnes of our 3D printed calcium carbonate to absorb 1 tonne of CO2. This is equivalent of absorbing all of the CO2 emitted from one fuel-efficient car with an annual mileage of 4,000 miles. The conclusions drawn confirm that our project would have a positive impact on the wider community.
We also produced a design for the nozzle section of our 3D bioprinter. Our initial ideas began as a simple double input chamber to isolate the bacteria from the external environment, but this thought process led on to the development of a disposable nozzle, which would mix the bacteria and hydrogel by vortexing the two streams. This would help reduce calcium carbonate buildup and prevent clogging of the system. We sent our initial design to the IGEM team at Ashesi, who very helpfully sent feedback and improvements to both the vortex mechanism and overall shape of the nozzle to optimise the natural draining flow of the ink. This led to what we believe is a viable design for the future implementation of a section of our 3D bioprinter. An integral part of our project has been our collaboration with our IGEM partnership team from UCL. Together we were able to perform flux balance analysis so that we could gain more information on our enzymatic and metabolic pathways. The result of this fruitful collaboration, with consistent weekly meetings, was obtaining vital information on genes we could knock out in Bacillus subtilis to maximise the carbonate production within the process. The data acquired has led to critical insights into the synthetic biology of our project and will prove incredibly useful for any future research into CalcifEXE technology. Although currently we don't have hard evidence for protein expression due to the limited time within our labs, our multiple modelling projects and biological concepts that this project have resulted in proves that we have hit our targets and beyond, particularly with the modelling and engineering aspects.
The last few months of the COVID-19 pandemic has seen multiple appeals to follow the science. The public, however, has been bombarded with conflicting messages about health and safety, which overall has only diminished faith in science. We believe that expanding upon the two-way dialogue between scientists and the general public in a clear and non-patronising way couldn't be more timely. We decided to make spreading the wonders of synthetic biology to the wider community at the heart of our project. We believe we have achieved gold medal standard educational content through a widespread variety of videos, infographics, lectures, and even a children's book. We wanted our top priority to be presenting educational material in as engaging a manner as possible. Throughout the project, we created multiple informative videos in an appealing format, ranging from the topics of climate change to biophysics, coral reefs to genetics. These videos could hopefully help people with little scientific background understand the joys of science, as well as what research is occurring around the world. Thankfully, we managed to get feedback on our videos from the City of London School to make sure they were at the correct level of difficulty and fun to watch, modifying our output on the opinions given. We also set about making professional and creative social media channels on Instagram, Facebook and Twitter, where we posted infographics explaining where we are at with our project, as well as the concepts behind what we are doing. In order to improve the accessibility of our educational material, we used dyslexia-friendly fonts as well as white writing on dark backgrounds so that it was available to everyone. To make sure we were targeting posts at the correct level, we released multiple surveys to gauge a response. From the numerous answers we received back, we were then able to adapt the content to the target audience. Due to COVID, university courses have had to adjust to the social distancing regulations by creating online content for students. We really wanted to assist our professors with this daunting task, and so throughout the project we helped them by making content they could present to their classes, such as a presentation for a bioethics and research skills module and another on VBNC cells. From everything we learned over the project about adapting our communication to suit the audience, we wanted to apply the knowledge to something important. We didn't want to forget the real future of science, younger generations. The children of today will be the ones developing scientific research even further, and so we wanted to help some of them discover the marvels of synthetic biology early on. We wrote an 820-word children's picture book called The Brilliant Biologists, which celebrated diversity within the community, as well as introducing biological concepts in an easy and creative way.
Due to the global COVID-19 pandemic happening during our project, we didn't manage to complete all we'd hoped for, so now we would like to take some time to let you know what we would have done if we had all the time in the world. Frustratingly, our Bacillus thuringiensis never arrived to be used in our co-culture. This non-ureolytic bacteria would have theoretically made the pH more optimal, enhanced calcium ion consumption, as well as providing an increased surface area for nucleation. We would have loved to have performed some test experiments to see if our co-culturing plan would have successfully increased the yield of calcium carbonate production, like we hoped and as was supported in the literature. Although we attempted to transform our plasmids into Bacillus subtilis, we did not have any success, and unfortunately, we didn't have the time to properly troubleshoot the problem. We would also have loved to overexpressed and purified our enzymes from E. coli to investigate enzyme activity in vitro, but again, alas, no time. As well as this, based on the single gene deletion simulation in Bacillus subtilis performed by our partners at UCL, we would have liked to have knocked out a number of non-essential genes, but our supervisors have since told us that this would be a humongous task. We would need to model further knockout simulations to better inform future lab research, but it looks like a promising next step. And of course, we would have liked to have reached the point in the lab where we felt confident to combine our hydrogel with our bacteria, as well as to record the rate and yield of calcium carbonate precipitation, maybe even record the carbon input and output to quantify the carbon mitigation of our method and its overall carbon footprint. That could be done with activation experiments. Supervisors, can we come back next year? That's only what we hoped to have done during IGEM if our lab time hadn't been limited. For the future of this project, however, we imagine much more. To continue our project, it would be necessary to investigate into its implementation onto the seabed. This would involve coral attachment tests and experiments into the removal of the GM bacteria before it's put into the environment. We hope that the research and coding we have developed will help further the future IGEM teams who are interested in solutions to this global problem. We know the more we investigate, the more we'll find to explore. All we can hope is that somewhere in the future there will be lots of happy CalcifEXE corals growing all around the world.